but we've broken it into various different topics. At the end of each topic, there's a questions and answers session. If you have a question, what we'd like you to do is to put that onto the chat, and they will be looked at because we have a very short question and answer sessions after each of the topics. Then at the end of the whole event, we have a panel discussion, where we've invited four panel members have kindly agreed to join the panel, where there will be we put a set of questions to them that we'd like to be able to get some answers for, if possible, from industry. So that's where we are. So we aim to finish sort of around about 12:30 UK time, obviously an hour later for European time. So okay, so I'll just run you now through the context really of NEXUS, what we started to aim to do at the beginning of the project. So why do offshore wind farm service and maintenance operation require improvement? So the operation and maintenance of current offshore wind farms represent a significant amount, 20 to 30% of the total wind farm life cycle costs. At present, most of the offshore wind farms operating in European waters are quite close to shore, under 40 nautical miles, but the trend is to move these further offshore. There's also a trend for the wind farms to be larger, with greater distances to the turbines. So these trends result in larger travel distances, often more adverse conditions for the vessel and crews, and therefore possibly more downtime for the failed turbines, and obviously increasing the cost of the maintenance as well with the distances. The transportation of technicians, equipment and spare parts is mostly done by service vessels, and it accounts for the majority of the total O&M expenditure. Therefore, this was seen as a clear target for an area of improvement to reduce the O&M burden, and this is what NEXUS has been working on. There are also major opportunities to improve the O&M by relying on being more proactive and looking at data-driven maintenance and operation. Planned operations and being less reactive to the failures as they occur, and a large part of the project has been involved in this. So looking at what NEXUS has done, so as I said there, NEXUS aims to improve the SOV operation efficiency. So it's pursuing a new vessel, it's looking at game-changing technologies, further advances in O&M, and carrying out business analysis and modelling of the complete O&M services. So I'll just take a look at the high-level objectives at the beginning of the project. So the aim was to reduce the logistic costs for offshore wind turbine maintenance by 20% and lower CO2 emissions by 30% using a new design of wind farm service vessel. To enable robust decision making resulting in reduced costs and effective management of business risks of the service vessel. To capture robust design requirements for a new design of wind farm and develop service vessel for operation in the North Sea. The new vessel concept for servicing offshore wind farms to satisfy and set robust design requirements. And develop specialised safety regulations for wind farm service vessels to improve cost effectiveness and operational flexibility. Potentially inhibited by the current generic safety rules. Okay. So, and then a very important part of the end is to compile a business case and modelling of the whole system for a new wind farm service vessel. So the partnership of NEXUS, we started the project in November 2017, and it's due to finish at the end of this month. The NEXUS consortium has brought together the following partnership from 4 different countries. So Arctic is the coordinator. We're involved in the management, communication and dissemination of the project. We have Kongsberg Ship Design. We've got GONDAN, who's a shipbuilder. We've got Global Marine Group providing the operational maintenance advice and support. We've got SINTEF Ocean, who've been providing the testing of the vessels and further research. And we've got University of Strathclyde, who play a big role in the operational requirements, safety management, and also, as I said, the business school modelling for the whole business. And then we've had DNV, who are the Classification Society, have been looking at the safety regulations and seeing whether they can be modified and improved. Okay, so a quick run through there of the context of the project. What I'm going to do now is to pass over to Gerasimos, who's going to be taking us through with his team, looking at the requirements, effectively, of the project. Okay.
Many thanks, David. Good morning, everybody. My name is Gerasimos Theodokatos, and I'm professor of safety of marine systems at the Maritime Safety Research Center of the University of Strathclyde. Let me share my screen and the presentation we prepared for today. So I expect that you can see my screen now. So the title of this presentation is towards next generation service offshore vessels, how to enhance operational efficiency and short-term operation and maintenance planning, as well as safety. And the presenters today will be myself and Dr. Iraklis Lazakis, who is my colleague at the Department of Naval Architecture and Marine Engineering, and also other contributors to this presentation were Mr. Odd Karsten Olufsen from DNV and Mr. Svara Torben from Kongsberg. So I will go through the contents of what we'll present today. We start with offshore wind farms, just summarizing the current status and future outlook. We'll continue with our work on enhancing SOVs efficiency. Then we present also some work and a tool we designed on short-term operational planning and maintenance. And we'll conclude with a safety enhancement of SOVs design and operations. So my colleague now, Iraklis Lazakis, will cover the current status and future outlook. Iraklis, can you take care of the control?
Thank you, Makis. Actually, could you control the slides as such? And move on, no as we move on. Great, thank you. So good morning, everyone. From my side too, my name is Iraklis Lazakis, and I'm a reader at the Department of Naval Architecture, Ocean and Marine Engineering at the University of Strathclyde. And initially, as part of the NEXUS project, the very early stages of the project, we went through a number of material and resources in order to try to identify what is the current status and future outlook when it comes to the offshore wind sector, and also what are the vessels being used, what are the current regulations, etc. So this slide summarizes all this work. Initially, we started considering what is the current energy market and the ongoing projects, both near and far offshore, floating wind turbine installations. Then we had a look at the national and international regulations, guidelines, and policies which are available in the sector or may affect offshore wind sector as well. Also considered the wealth of experience and lessons learned from the oil and gas sector, as well as the existing operations and maintenance, CAPEX and OPEX tools. Eventually, we also examined the main industry challenges in relation to operation and maintenance, also in particular novel vessels and equipment being used, and the logistics related to offshore wind. And finally, there were options for different vessel characteristics or combinations of vessels to be used within the O&M within offshore wind as such. If we move on to the next slide. So in this respect, the main findings was, well, as we're expecting, the offshore wind market and employment does continue to grow exponentially within the UK, Europe, but also all over the world, in China, US as well. Among the crucial parameters to consider for any particular offshore wind project and the vessels to be used within such a project are the offshore wind farm water depth, the average wind speed, and in general, the weather and the meteorological conditions, the distance to the O&M hub port as well. Also, we found out that there needs to be a consistency among the various international and national regulations which are in place for specialized vessels, especially the ones used within the offshore wind. And thus now we move on to having dedicated vessels purpose-built for the offshore wind sector. On the other hand, among the main considerations for offshore support vessels, these continue to be the technician's comfort, the high maneuverability of the vessel, the seakeeping characteristics, the speed, the fuel consumption, and also alternative fuel sources for the main propulsion and auxiliary needs for support vessels. Finally, we consider that there should be a number of tools, a suite of novel software tools, which will be needed for both for longer term, but also for short-term O&M decision making, which need to be streamlined to a particular location of a wind farm and the particular needs for the offshore vessels that will be used within this wind farm.
So thank you, Iraklis.
Yeah.
So if I continue with our work in improving operational efficiency, one of the objectives of the NEXUS project, as David described in his presentations, to increase the efficiency, both operational but also the energy efficiency, as well as reducing CO2 emissions. So initially, as a part of work package 2 and in collaboration with Kongsberg, we investigated a number of alternative technologies that can be used for enhancing the efficiency of SOVs. And we identified 3 technologies with potential for further investigation. We found out that solar energy, solar panels, photovoltaics can reduce up to 3% the fuel consumption based on the baseline SOV that we consider in the NEXUS project. And this by only using the available area and not changing the design of the vessel. One of the potential technologies that can lead to energy efficiency but also to zero emissions is the hydrogen, and this certainly will constitute one of the technologies that will be investigated in the future. But currently there are huge challenges related to cost and logistics. The DC direct current grid and variable speed technology was found very beneficial for SOV operations, and basically based on actual measurements from the baseline vessel, we found out that there was an improvement of fuel consumption considering operating profile, a typical operating profile of this vessel. Finally, the wind power was also considered and also identified as a technology with potential for the cases of floatels. Then one of the main activities was to enhance, jointly enhance the energy efficiency and operational efficiency. And then in this respect, we ended up in a concept that combines the predictive power management along with short-term operational planning. And the concept actually includes starts with a task assignment, proceeds with planning of the tasks, of the various tasks, and then also includes the power management and the control of load sharing and control of the power plant components. Just demonstrate a bit better the idea. In the top layer, we ended up to include a mission planner, and a mission planner converts a mission in a list of tasks. So then having this list of tasks and going through an optimization mode, we ended up in a timeline. This timeline converts in an operating profile with regards to speed, operational speed, optimal speed versus time, and also the various modes of operation. For example, approach to a wind turbine, leave from a wind turbine, waiting, transit, so on. And then this optimal operating profile again feeds information to the predictive power management system, which actually optimizes both, in this way, optimizing both operational efficiency and energy efficiency. So one major constraints in that case is the weather conditions, and in this respect we need an accurate or some information for these weather conditions. In addition, the propulsion modes and the arrival departures times are considered also as operational constraints. Then one part of this tool is the short-term operational planner, and now again Iraklis will lead us through this tool. The optimizer, an optimization tool, was developed in this particular case. So Iraklis, can you please explain the function of the tool?
Yeah, thank you, Erasmus. So in this respect, this is the development of the short-term operational planner, and as part of NEXUS project. And going into the particular details of this software, this was developed as a tool in order to have very short and daily, actually, and very quick decision making. So this particular software can be run depending on the particular input, can be run even on the day, early morning of the day that the actual operations will take place. The main purpose of this tool is to optimally plan the maintenance operations using a vessel like an OSV, a CTV, or a combination of different vessels to accommodate the daily needs of the offshore wind farm operations and maintenance. As input in this tool, you can use the weather conditions, the particular weather conditions within the location of the wind farm, the particular wind farm attributes in terms of the specific location of wind turbines, the wind turbines failure attributes as well, the vessel characteristics, and also as a final input, the particular fuel that will be used to run the vessels. Now, the output of this tool is related to the particular very specific maintenance scheduling in terms of what is the sequence that a particular number of wind turbines need to be repaired, let's say, need to be maintained. What also will be the particular vessel's routing for these specific wind turbines on the day of the operations. And of course, what is the fuel consumption for these particular vessels. Now, within this tool, we have also integrated an additional input in terms of the drop-off and pickup sessions. So in this case, a particular vessel, which is used for the daily O&M, can wait for to drop off the crew on a wind turbine, then can wait either alongside the turbine, or can move on to a standby location and then proceed to pick up the crew and transfer them to the next turbine, etc., in order to consider the optimal weather window and increase the availability of the vessels and eventually minimizing fuel consumption as well. Now, if we move on to the next slide, Gerasimos, if you could move to the next one. Yeah, thank you. So in this case, that's an example of how this particular tool will work, having a number of different inputs on the left-hand side, and how this can then be used to provide the optimal routing within the wind farm. In this slide, we can see a couple of applications and case studies, different scenarios actually, which we run for the operational planner. On the top right corner, you can see a scenario where an SOV is used only. In this case, we can see that there are a number of wind turbines that need to be maintained. These are shown with the red dots. And then we can see how the operational planner provides the way in and out, and also how the standby locations can be shown as well in order to optimally maintain these turbines and provide the optimal routing, but also the optimal fuel consumption. At the bottom of this slide, we can see again another scenario. We have a different number of turbines that need to be maintained, and how this, in this case, and how this also can be serviced by the use of an SOV. In the next slide, if we move on to the next slide, we have a couple of other cases as well. Again, with these cases refer to different turbines that need to be maintained, and how at the top right corner you can see that only CTV or a number of CTVs can be used, while at the bottom of the slide you can see a combination of an SOV and the CTV can be used as well to provide the optimal routing within the wind farm layout to service the specific turbines that need to be maintained at that particular day, and again providing the optimal fuel and the minimal fuel consumption for these vessels. What I want to highlight here is that in this case, these different scenarios are not comparable to each other, as they refer to different case studies, different types of different number of turbines that need to be serviced and at different particular locations. However, these examples show how this tool can be used and can be also streamlined and adapted to the particular needs of a wind farm and wind turbines to be maintained. And that's it from my side. Gerasimos, back to you.
So I'm conscious about the time. I will try to be quick. So the last part of this presentation covers the safety enhancement of the SOVs and their operations. So that was a part of the work performed with from the Maritime Safety Research Center and DNV, and also Kongsberg also participated and contributed to the work. So in this respect, we started for a safety analysis of the baseline design and along with proposed technologies, and we included in the safety analysis the power management system, including power generation, distribution, control, batteries, and predictive power management, the dynamic positioning system, the motion compensated gangway system for technician transfer, the interface between the SOV and the wind turbine, the interface between the SOV and the daughter crafts with different David systems. We also investigated the cybersecurity vulnerabilities, and at the end we use the results in order to enhance the safety management system and also to map regulatory and class rules that need to be amended or added in order to cover all these requirements. So we'll start with the safety methods we use traditionally. Maritime, the industry uses methods, for example, traditional methods, for example, FMECA, ATA, HAZIT, HAZOP, and however, these methods do not, although cover critical failures and can cover reliability problems, they cannot cover all unsafe scenarios. So in this respect, and in the NEXUS project, we use the more modern methods. For example, we use in this particular case, we use the System Theoretic Process Analysis, STPA, which was developed from MIT and used a number of systems in aerospace and avionics. And then in this particular case, we followed the STPA process to identify unsafe control actions which may lead to an accident or a hazardous scenario, the causal factors of leading to these unsafe control actions, and then in order to develop safety requirements for all the areas that I mentioned in the previous slide. Moving on, a causal factor is a factor that basically leads in an unsafe control action, and an unsafe control action can lead to a hazardous status. For example, a causal factor is the gangway operability suddenly reaches the limits or alarms are deactivated. This leads to an unsafe control action, which is to retract the gangway, and then this may lead to hazardous states, which maybe gangway. If gangway is retracted, then technicians are being when technicians are being transferred. In this case, we can when we map and identify causal factors and unsafe control functions, we can propose prevention measures, both for design and operation, and mitigation measures, which of course need to be only applied after the unsafe control action occurrence. In addition to this, we consider causal factors from safety, the safety assessment, but also for the cybersecurity threats, and all lead to a more holistic mapping of the safety requirements and safety during operation and during the design of this vessel. We included the interactions of the SOV with all the actors, for example, with the shore, with the crew transfer vessel, with other ships, with the daughter craft, and with the wind turbine, as well as the individual interaction between SOV and each one of these actors. We also consider a number of operating modes, for example, rest, transit, maneuvering control of SOV, the interface control during the deployment of the gangway or use of the gangway, the interface control in case of deployment of the launch of the daughter craft or the crew transfer vessel, and the control during these operations. So this end up in, of course, in a very large envelope, and we needed a more automated way to carry out safety assessments. So in this respect, we developed a tool, a semi-automated tool for using the STPA method. So after when the user includes the safe control action, then there is an automated way of producing the causal factors from specific lists that we developed in this software, in this application. And then this leads to a number of functional requirements, and apart from that, also related either to design or to the operation. And then we ended up in proposing preventive or mitigating measures, and then ranking the impact, which means the severity and the cost effectiveness of the measure ending to prioritize the proposed measures. So this led to a very large number of requirements in specific. This provides some numbers, for example, for the SOV bridge and dynamic position operation. We identified 145 requirements. For the davit operation, 38 requirements. For the gangway operation and technician transfer, 88 requirements. For the daughter craft operation, 27 requirements, and for technician transfer to daughter craft, 16 requirements. So that the final state of this analysis to map the requirements. So there was work carried out by DNV. So they considered the requirements, and then they consider also the design rules and mapped which requirements are covered from the existing rules and class, the existing regulations and class rules. For example, the class rules of DNV and the regulations from SOLAS, and which requirements are not covered from regulations and rules, in which case recommendations for amendments of the rules were proposed. So that concludes this presentation. I would like to thank you all for attending this, and for further details you can contact the contributors of this presentation. Thank you very much. David, back to you.
Okay, I think we pass over now quite quickly because of the time. I think Leslie, are you leading this? You're leading this session, aren't you?
Yes, I am.
Okay, thanks. I'll pass to Claire.
So good morning, everyone from Glasgow. Hopefully you can now see my screen, because I'm going to lead this session, which is about the holistic modelling framework that we've designed in order to achieve the objectives of the overall NEXUS project. So I'm going to kick off by telling you a little bit about the new model that we've created within NEXUS, what it is, why we approached it in this particular way. I'll then pass to my colleague Vidar from Kongsberg, who will describe why some of the KPIs that our model support are particularly important from the commercial perspective. And Vidar will also describe some of the logistical concepts that the designers at Kongsberg were considering. And then my colleague Ewan, also from the business school at Strathclyde, will talk about some analysis using the model that I introduced for some of the logistical concepts that Vidar describes. And then at the end of the session, I can make some concluding remarks, and we also should have some time for questions. So the model I'm going to describe is a new one that's been created in NEXUS. We've called it ISPOC, where the acronym stands for Impact of Strategic Predictive Operational Capability. And the name we came up with basically describes the purpose of the model. What we are trying to do is predict the operational capability of logistical concepts that at the start of NEXUS still had to be designed, and to support that design process through the project in such a way that people could anticipate what the future offshore wind farm operations and maintenance ability to be serviced would be. So we've called it strategic because we're largely looking at a first order model in order to understand what are the key decisions that designers must make when shaping the vessel choices in order to be robust to future market conditions. And we've also put the impact at the front because we're not just looking at the technical performance of the vessel, but ultimately we want to think about it in terms of its business consequences, particularly the financial ones. So you might be asking yourself, why do we need another model? You know, Heracles, for example, has already mentioned about short-term operational planners. And I'm certainly aware there are many software tools for O&M modelling in offshore wind, both in practice, but also certainly in the academic literature. But one of the reasons we felt we needed a distinctive model is for the nature of the decisions we're trying to support through NEXUS. I say our purpose is quite distinct because we're thinking about new vessel designs for wind farms that don't yet exist. And we are in a situation where there is not some user requirement specification that the designers are working to. So if I was comparing the purpose of our model compared with, for example, the one that Iraklis mentioned earlier, I can think of it very conceptually in terms of this artistic impression, in terms of when we start making the forecasts. So for example, Iraklis mentioned making it during real-time operations.
Hi, Leslie. It seems to be that you have dropped off. Shall we jump through to Vidar and then we can come back to Leslie? Leslie, we've got you now.
Yeah, if I drop off again, I seem to come back in just a moment. So I'll just carry on and let me know if you can't hear me, because I'll even try keeping speaking. Thanks. So I was just leaving off at the point where I was saying that Iraklis was making short-term forecasts, thinking about, for example, forecasting the next day when you're actually in an operational context using the vessel. But we're in a situation where we're way back in terms of conceptualizing the design of a vessel, and we're trying to make forecasts well into the future in terms of operation. So our forecast horizon is very, very different. But as you can imagine, the data demands we will need in order to feed these models is also quite different, because we're in a situation where we don't have the granular data that you might have when you're actually in an operational context. So from the ISPOC point of view, what we're really doing is we're focusing on trying to support decisions about design choices of logistic concepts by forecasting what their future operational capability will be. So in that sense, if we take the perspective of the vessel designer, we're thinking very much about how we make choices internally to the company that will cause positive impact on the external business market for offshore wind in future. However, from a business perspective, one of the things is we don't know what the futures will be. And as we know, there's always shocks to the business environment. So one of the things we also wanted to build into our modeling framework was an understanding or a visioning about what these future business environments might be. And if we could do that, it provides us with a mechanism for thinking about what might happen externally in future to help us think about, at the very least, the robustness of the choices we make now about the vessel solution. So how did we structure the ISPOC model for NEXUS? Well, this is quite a busy diagram, but this graph tries to sort of capture how we co-created the modeling logic together with the knowledge base of all our colleagues within the NEXUS project. Because people like myself, Ewan, we come from a business school. We are not experts in the marine environment or in offshore wind, but we do know about modeling. So what we were trying to do was understand the knowledge about vessels, the environments they have to work in, the business issues, the issues to do with manufacturing and regulation, and try and consolidate these at a sort of first order level so that we can understand what some of the key variables would be and how they interact with each other. So in this diagram, there's a number of nodes in this network. They have 3 different shapes. The ones that are in white and have the hexagon shape, they correspond to things like CapEx, OpEx, emissions, income. So in some ways, these represent the KPIs that are the impact that we are trying to effectively measure at the end of the day with the model. In the rectangles or boxes, we actually have decisions, which represents the actions that are controllable to our partners within NEXUS. So some of them, like things like the transfer capability, Again, colleagues later this morning will talk about the transfer mechanisms that might be chosen or selected between when designing the vessel, all the way through to choices about, for example, the day rate that's actually charged for the vessel downstream when it goes into market. And then in the diagram, there are lots of oval nodes, and these oval nodes represent all the uncertainties that we have in the problem. And it's fairly typical, this diagram, that we have a few KPIs we're trying to, let's say, optimize. We have a number of decisions, slightly more decisions that are under our control. And here we only represent, say, the big major decisions. But there's many, many more uncertainties in both the environment, the way the vessel will be operated, and also the way it will be made, the regulatory environment, what the competition is doing in the market, and so forth. Not to mention what happens in future in terms of government policy, fuel prices, etc., etc. So this model was very, very important to us because it allows us to start to articulate where we can control choices within the NEXUS world and where we have to make these choices robust to uncertainties that are as yet unknown. It's also important because it allows us to understand the relationships between different variables and which ones are particularly important variables. So when we build the model, we actually use a mathematical model. We've chosen to build this iSpark model as an analytical model, drawing on established probability theory, in particular queuing theory. Now, why did we choose to build it as an analytical model rather than as a big simulation tool? There was a number of reasons. One is that it allows us to express the relationship between all these uncertainties and choices and our KPIs, and allows us to do that very explicitly and to understand the nonlinear relationships that might happen in the system between all these variables. Also, by building it as an analytical model grounded in, let's say, an established probability theory, it allows us to have a very coherent and means of understanding the integrity of the way we represent uncertainty in the model. The other reason for us is it also allowed us to, say, have a good first order approximation to this NEXUS world that allowed us to span, if you like, some of the key engineering decisions with some of the business consequences without getting, let's say, too detailed in either the business or either the engineering, but to try and balance the two. Now, I'm not going to show you the maths of it. In a little while, I say Ewan will share some of the outputs, but let me just try and summarize some of the key features of it. Basically, in the right-hand side, I have a very simple framework, which shows the KPIs. And within the iSpark model itself, we largely have a set of KPIs that relate to the productivity of the vessel. And in the little box at the left-hand side, that just describes what some of these KPIs actually are. They relate to things like the productivity, which is the productivity of the farm, because ultimately we're looking to see how well the vessel will service the farm in getting any failed turbines up and running again. It's about the capability of supporting planned maintenance as well as, of course, unplanned maintenance. The very busy node in our graphical diagram related to turbines visited. So again, that's one of our KPIs. And then we have other KPIs related to the utilization and workability of both the vessel and the technicians. And if from the business point of view, we want to translate these into cost or emission and other KPIs, then we can combine the output from the direct queuing theory model in iSpark with other empirical data from cost and emissions to actually put a valuation on our productivity values. And in the iSpark model itself, it takes a number of inputs, some of which are assumptions we make about how the vessel and the technicians might have their different working practices. So, for example, the length of the working day. And again, in our model, we can play with that to experiment with different options. And again, a feature that's quite distinctive to the iSpark model is this notion of something called vessel productivity windows. So in other words, we're not in the same situation that Heracles mentioned earlier. We'll not have real-time weather data coming in to feed our model. So what we're having to do is to characterize wind farms, in some cases maybe existing wind farms or potentially future wind farms, in terms of, for example, weather windows where the vessel will be able to operate. And in order to be able to do that, we need to have some information that can characterize at a high level key characteristics of that operating environment in terms of things like wind speed, wave height, duration of peak waves. And we also have to have some characteristics that describe the vessel's operability. In other words, its ability to be functioning in different sea states. So at this point, what I will do when talking about the vessels, I'm going to pass now over to Vidar, and he will describe these vessels and some of their operating characteristics. And I say Ewan will come back later and describe some of the analysis. So over to you, Vidar.
Perfect. Then I will just open my screen. I believe you see it. Thank you. I will just then run through how we have done the ideation and down selection of logistics concepts to be run through the ISPOC modeling. The starting point and the basis for the NEXUS project is a holistic view on OM and logistics, where we look at cost, safety, and environment. The targets of the NEXUS project is basically cost and environment, but we need to do that keeping in mind safety. The modeling and planning capabilities that have been now presented allows us to line up and plan for lean operations and do time and resource management. These are key to manage environment and cost. Knowing how we can best do operations then provides a basis for simulation and configuration of power systems, and also quantifying the energy needs, enabling us to assess alternative energy applications. In terms of cost, we obviously have the productivity, meaning how fast you can do a type of operation, the weather window, meaning the extent of time that you can operate, and then time and resource management. What is a bit unique to the holistic view is that we do not only model the performance of the vessel, we put also into the context of the overall operation and look at associated costs. To the left here, we have a generic example of an SOV operation, where we see that the vessel itself is roughly 1/3 of the cost, the vessel and the marine crew. A half of the cost is the productive technician time, which is a desired cost. And then important cost elements are also lost technician time, partially due to lacking planning, partially due to restricted weather windows, and also lost power production in the wind farm. These associated costs are also factored into the modeling that we are doing, which means that the optimal overall concept might not necessarily be the cheapest vessel, but the one that we can justify performs best, including these associated costs. Starting at establishing logistics concepts, we're breaking down the duty into its elements. O&M can in principle be done by offshore operations, meaning technicians being housed offshore, or shore-based operations shuttling to and from shore. The latter is not a core part of the NEXUS scope, so our focus has been on the offshore solutions. And the duties of the logistics setup is then based on housing technicians, which could be done by means of an SOV being a movable asset in the field, or a flotel being a moored or otherwise fixed asset in the field. We then need to do transfer of technicians to the turbines, and we need to do transfer of equipment to the turbines. In the case of an SOV, that can be done by the SOV being equipped with a gangway or by daughtercrafts. In the case of a flotel, you need either a separate SOV or CTV solutions or daughtercrafts. In terms of equipment transfer, the Swiss Army knife of the SOV can do that with its own crane, whereas in the flotel solution, we need separate vessels to do that. In the future, we also believe that drone operation support will be increasingly a relevant duty of these logistics setups. Looking at these fundamental tasks, we then populated our toolbox of flotel, various sizes of SOVs, CTVs, and daughtercraft, and also transfer systems, crane capacity, and fundamental accommodation function. We then configure different logistics setup comprising one or more assets each configured to be capable to deliver what we believe is the needed capacity in the field. In terms of SOV concepts, we also assessed various hull forms, more or less exotic, having different buoyancy distribution, different water plane area and center of flotation, thereby having different capabilities in terms of resistance and motions. This was also considered in the context of us wanting to assess not only the typical midship mounted gangway, but also the prospect of a bow mounted gangway, as we will touch upon later on. We then, for each of the concepts, did a parametric design to scale them, ensuring that each concept has the necessary areas and volumes to deliver the capabilities required. And then we had scaled concepts that we could put through analysis. For some of the concepts, we all looked more into practical implications. Here, a case with the bow-mounted gangway with a forward superstructure, the same concept with a central superstructure, obviously affecting how we can arrange the vessel internally. And also here, like a SWOT flotel concept fixed to a fixed monopile structure offshore. Then putting this through analysis with respect to resistance, motions, productivity and energy demands, we were looking at knowledge from past operations of similar vessels. And we see that generally, of course, O&M operations consist typically of cycles of roughly half an hour's duration, where you transfer between turbines, connect to a turbine, transfer technicians and equipment, and then move on to the next. This is pretty much similar to a ferry operation, more than a typical cargo vessel operation. What we found in our analysis, broadly speaking, is that the more exotic hull forms generally tended to have more resistance, especially at higher speeds, whereas the differences at more moderate speeds, the type of speeds that you operate with in a wind farm, were minor. In terms of motions, the more exotic hull forms tended to sometimes perform better in certain ocean environments or sea states, but poorer in others. In conclusion, we found that the more exotic hull forms did not provide, let's say, robust benefits overall, and we gravitated towards a hull form that is for sure novel, but still fundamentally a monohull of a fairly conventional sizing. It's a double-ended monohull. It will typically be equipped with 2 azimuth thrusters forward, 2 azimuth thrusters aft, and the advantages of that configuration is increased maneuverability, allowing for better acceleration, turning and braking power, and also better station keeping efficiency by the fact that you can use the main propulsors to an optimum manner in DP operations. Also, the symmetry and more uniform component choice should allow for simplified engineering. And in terms of drawbacks, having forward thrusters would be some drawback at higher speeds, but considering an SOV operation, most of the operation is at moderate speeds, where the benefits in terms of maneuverability much outweigh the disadvantages of forward propulsors. So this became our preferred concept hull-wise. Then looking at means of transfer, we see that typical SOVs do have an extensive use of daughtercraft, here indicated with the red lines over a period of close to half a year. But, and then the gangways are being used for the blue bars. So daughtercraft provides an important flexibility. At the same time, it introduces a vulnerability, as we see towards the right-hand side here, where there is a period of a few weeks where you cannot operate daughtercraft due to inclement weather conditions. So in conclusion, we found that we would probably be bound to have a concept including a gangway apart from daughtercraft. And that led us to suggesting concepts for the icebox analysis with direct transfer SOVs with gangways based on the double-ended monohull with the side gangway, the conventional setup, and the more exotic or new novel setup of a bow gangway. Then for reference, we maintained a SWOT SOV design as well, also in different sizes in terms of technician count. And then we wanted also to compare that with non-direct transfer SOVs based on monohull, SWOT, and float hull designs. So these are the designs moving into the icebox analysis, which I believe Ewan will present more of the results of that. I pass the floor to Ewan.
Okay, thanks, Vidar. I'll just share my screen. Okay, hopefully you can see my screen okay. So I'll just show a small selection of analysis using the icebox model that Leslie set out earlier to investigate the performance of the logistical concepts that Vidar has been describing. More generally, the analysis was run with data drawn on existing wind farms. So we used Dogger Bank and Race Bank with estimates of demand for different types of maintenance jobs and the durations of these, as well as the vessel operating characteristics, in order to generate the productivity windows that Leslie was discussing earlier for different times of the year. So this slide is investigating the performance of 3 alternative transfer methods. So we have the direct transfer SOVs, the indirect transfer SOVs, and the flotel option. And in each case, we're looking at the 2 hull designs that Vidar mentioned, the double-ended monohull and the swath, giving 6 logistical concepts in total. So these figures give a sense of the type of analysis that we've been carrying out, investigating a number of different logistical concepts and assessing these against a number of different KPIs. And we're looking here at the 6 KPIs that Leslie mentioned earlier on that collectively give a broad perspective on the performance of the different concepts. Some of these, like the productivity, which is shown in the top left here, will feed directly into the costing assessments in the business case later on. So the top set of bar charts show performance. Show performance against the 6 KPIs, with each bar chart focusing on a different KPI and showing the performance of the 6 logistical concepts. The bottom charts here, the radar charts, each chart is focused on a different logistical concept and shows the relative performance across the 6 KPIs for each of the 6 concepts. Some key messages we can take from this. If we look at the productivity, for example, we can see that there are differences, but they're relatively small between the 6 different concepts. But if we then look at how the capability of the different concepts would feed into the capability to conduct annual planned maintenance, we can see that there are substantial differences, particularly the direct transfer vessels, which are shown by these 2 bars, are substantially outperform either the indirect transfer or the flotel options. And additionally, we can see that the monohull outperforms the swath design on most KPIs, as Vidar was alluding to in his slides. Another set of investigations we looked at was investigating the effect of different daughter craft capabilities, and again looking at how changes to the daughter craft capability would influence these different KPIs. On the top, we're looking at the effect of a higher spec daughter craft in terms of being able to operate in more extreme conditions. So a significant wave height going from 1.8 meters to 2 meters. And on the bottom, we're looking at the effect of using faster daughter crafts. So looking at speeds of 30 kilometers per hour up to 46 kilometers per hour. Throughout all the analysis in this slide, we are looking at the medium double-ended monohull side transfer SOV and using Dogger Bank weather data and site data, rather, more collectively. The key messages to take from this, I appreciate the numbers are going to be quite small, quite hard to make out, but looking first at the bottom set of plots, where we were varying the speed of the daughter craft, we see that there are only very slight differences in terms of varying the speed of the daughter craft. So using a faster daughter craft, we wouldn't expect that to have a substantial impact on the overall KPIs that are being recorded. Looking then at the top plots, again, there's not massive differences in terms of the productivity, but if we look at the annual planned maintenance capability, we actually see that going from a daughter craft of 1.8 meters to 2 meters would give you an increase of approximately 3.5% in terms of the number of turbines that you could address with planned maintenance throughout the course of a year. So we see that in that case, there is a more substantial effect on the performance of the logistical concept. And then the final analysis slide I want to show is a breakdown of utilisation. So here we're looking at utilisation of the vessel on the bottom and utilisation of the technicians on the top. And these figures are showing a breakdown of the utilisation of the vessels and technicians that we can use to examine the allocation of these resources and assess whether the allocation is appropriate for the wind farm that they're being deployed on. In these slides, again, we're just focusing on the double-ended monohull SOV, and we're looking at the small, medium, and large sizes of that. In all of these figures, the y-axis represents a whole day, and each of the coloured areas then shows the percentage of the day that is spent on different types of activity by technicians and by the vessels, respectively. So for the top slides, the yellow areas show the percentage of time that is being spent by technicians on maintenance. The blue areas are showing the percentage of time being spent by technicians in transit, and the green areas are showing the percentage of time that is unused by technicians. We can see broadly that the proportion of unused time decreases certainly between small and medium SOVs. We can see that for the larger SOVs, the blue area has increased, so the time spent on the vessel on transits has increased, and we can use this information to try and assess how appropriate the technician deployment is to the size of the wind farm. And on the bottom set of plots, we're then looking at the vessel activity. Here, the blue areas represent transits, the orange areas represent transfer, and the purple areas represent the remaining time in a day that's unused. And again, here we can see that the broad picture is that the remaining time in the day, the unused time in a day, decreases as we increase the vessel size, and the vessel spends more time on transfer and transit activities. So again, we see in this case that with the larger vessel, the larger SOV, we make more effective utilisation of that in this case. Okay, and I think I will now hand back to Leslie.
Yeah, so if you just go to the next slide, please, Ewan.
Yep, sure.
So I was just going to summarise, because obviously Ewan's just given you a flavour of some of the analysis that we can run, particularly looking at the productivity KPIs. in relation to some of the vessel concepts that Vidar has described. And if we go to the next slide, please, Ewan. And I think one of the things I just wanted to end on was a little bit of reflection about how we validated the model, because as we indicated, we are trying to forecast well into the future for a vessel that doesn't exist for farms, although in some of the test cases we've used farms that do exist, but for a situation that we've not actually applied the vessel in. So I just wanted to share a little bit about how we'd approach validation, because we can't necessarily do it in the conventional empirical way. Again, part of it goes back to our academic work and the fact that we're working with theoretical models, and we've made choices about algorithms in which to implement some of that theory into a software tool. And so there's been a lot of backroom work in terms of that mathematical proof and experimental analysis with those algorithms. But I think the other thing that's worthwhile flagging, maybe more importantly practically, is that I think in this ISPOC model, there's about 30 assumptions that we have made and negotiated, sometimes quite vigorously amongst the team. And these assumptions fall into basically 3 categories. There are a small set that are hardwired into the theoretical underpinnings of the model that are almost like, once they're signed off, we can't change these. Then there's a set of assumptions that we make modeling choices that are adaptable, but they do require a modeler like Ewan or someone else from the Strathclyde team in order to be able to adjust the model, in order to make sure these adjustments ensure we can contain the integrity of the underpinning probability framework. And then there are other assumptions that are more linked to the domain environment, things like I mentioned earlier about the length of the working day of the technicians or the vessel and so forth, how often it goes back to port, how long that journey to port takes. And these are all immediately and directly changeable. So I just wanted to emphasize that in terms of validation, I think one of the big elements has been this very, let's say, strong iterative negotiation of assumptions between, if you like, our modeling world from the academic side and what these assumptions mean in the reality of the real world as experienced by Kongsberg and other partners within Kongsberg. And I think the other thing has been looking at the credibility of the results, because within the sets of both vessel concepts and environments that we've looked at, we've included some that are quite close to what is the, if you like, the reference case in the contemporary world for offshore wind. So that also has allowed us to assess credibility and to explore things if things look a bit counterintuitive and we can't explain it by any of our assumptions. So I'm going to finish off there just now in terms of this modelling framework. As we've already indicated, later on this morning, some of our other colleagues from the business school will talk a little bit more about how we have used some of this within a sort of a wider business analysis, particularly looking towards the future of offshore wind. But at this stage, I'm just going to ask Matthew, you were keeping an eye on questions, and I think we still have a few moments for any questions about either this section or anything that Heracles and Marcus and Dave talked about earlier this morning.
Hi, Leslie. No, there's no questions that have came in, so I don't know if we want to carry on onto the next section, or if there was anything that anybody had now that they've got an opportunity to want to add it in very quickly.
Hi, it's Dave here. I was just going to say we could obviously we could still take questions as we go through. If we cannot have an opportunity to answer them in the webinar, we will aim to answer them after. So as we haven't got any, I suggest we move on now, because obviously we've got quite a tight time scale, if that's okay. All right, thank you very much to Leslie and Vidar and Ewan. So that was very good. So now we move on to the next section, which is research finding with respect to the baseline design SOV and its design manufacturability. I think Vidar, I think you're in this again. Is that right? So I think you're the
indeed.
Again. All right, thank you. Right.
Thank you. And I believe you see the screen. So I will then go through a bit on the findings relating to the SOV baseline design, reflecting key findings from the NEXUS project. And then Odd-Karsten Olufsen with the DNV Maritime Advisory will highlight some risk implications particular to offshore charging, And finally, Louis Morel, working with tendering and sales at GONDAN Shipyard, will comment upon the buildability and relative cost of the baseline concept. Broadly speaking, the ISPOC analysis actually created confidence in the medium-sized SOV, or let's say the basically established SOV concept actually being a favorable concept. So what we wanted to do, developing the baseline concept, was to look at how might we think different about SOV designs. So the fundamental concept as such is not changing, but execution, we want to explore new possibilities. When doing that, we build on the knowledge portfolio on our past designs, where we have used reference vessels, Edda Passat and Edda Mistral, which were delivered based on our design in 2018 to Østensjø. These are vessels 82 meters long, 17 meters wide, housing 40 technicians and a maritime crew of 20. Then deriving from that, the new baseline concept has a fairly new layout, utilizing the double-ended hull design, and also building on that by adding symmetry also in the above waterline design. The design is fairly similar in size, 1 meter longer, 1 meter wider. The size increase is mainly a reflection of the requirements for workability ever increasing in the business. But in terms of technician count and capabilities, it is still 40 technicians and 20 crew. What we see also from the ISPOC analysis is that it is very important to be able to scale the solution to the given wind farm. Furthermore, we see that in the future, economies of scale will probably also have a greater impact in this industry. So we envisage that we might move towards larger SOVs more frequently being used. So when thinking about the baseline concept, we wanted it to be scalable. And we use the symmetry to the full extent. That means we have symmetrical propulsion, and to maximize performance and utilization of the installed propulsors, we opted to redistribute the volume of the vessel and create a more symmetrical airdraft profile. The grey vessel in the back is the reference vessel, which also is very similar to most conventional SOV designs out there. And we see the green new design has moved the center of the airdraft towards the midship, and also reduced it lower down by mainly also lowering the optional helideck. So this provides for better utilization of the installed thrusters. The double-ended concept was further explored and verified through numerical simulations and also tank testing, which also led to notable improvements in the design and performance. In terms of the overall layout, we have the focus on symmetry and trying to facilitate scalability and minimize build cost. That means that we want to keep some parts of the vessel stable, whereas other parts could be scalable. The starting point of that is a midship logistics section. It comprises the main elevator case. It has a boat landing to starboard, a pallet handling system to the port, and then the charterer and ship offices in the superstructure. This section basically remains unchanged irrespective of scale of the vessel. Then towards each end, we have machinery sections in the bow and the stern. These are also largely remaining same irrespective of vessel scale. Then importantly, in between, in still what is the parallel midship section to a large extent, we create scalable sections where we can choose the extent of personnel. We can alter the number of daughter crafts, and also the packing area capabilities. In the center of the vessel, we also have an independently scalable service section. We see that there are longitudinal arrangements that allows us to alter the central section independently from the side sections. So this creates flexibility in how we execute and prioritize the use of volumes. And importantly then, we can basically lengthen the vessel or shorten it by prioritizing different types of capabilities depending on the project. Important also is that the vessel is basically symmetrical both along the midship and along the central line. That makes it far easier to reuse engineering, to reuse arrangements, which could provide for reduced lead time and higher reuse of engineering. A novel feature is that we have restacked the vessel. Notably, the packing area is moved down to the tween deck, which is often a bit underutilized area on these vessels. Typically, the packing areas are on the main deck. This is then extended with the logistics functions up. We have then notably made available the core and scalable parts of the vessel for the client areas, meaning all accommodation aboard the waterline, close to the midship, in the most comfortable areas of the vessel. So this is a very, let's say, charterer-oriented vessel, focused on comfort, apart from scalability. Then the more peripheral areas of the vessel is used for vessel systems. In terms of mission equipment, we have a stern-mounted gangway, or you could call it a bow-mounted gangway since it's double-ended, as a more novel approach. But it's notable that we can apply also a conventional midship mounted gangway without any alterations to the design as such. So this is an important flexibility. We have fitted the vessel with a boat transfer system that we will comment upon later on. We have notably stepless daughtercraft and CTV landing to the starboard, meaning you have movable ramps both at main deck and A deck level, where the lower one typically services daughtercraft, the higher one typically services CTVs, all stepless. On the port side, we have a pallet lift system. We have opted for the logistics, cargo logistics to be based on pallets, and you can easily land cargo with trucks, which is transferred into the packing area on tween deck. By making the superstructure smaller and moving it closer to midship, we have also allowed for lowering the optional helideck, thus lowering the center of gravity and largely reducing the air draft of the vessel. In terms of the mission equipment, the gangway on the stern is an alternative that we are considering based on the fact that wind farms tend to have ever higher landing heights. That means that pitch of the vessel will start to move the gangway platform more and more, which with a conventional gangway will have to be absorbed by slewing the gangway, and which could result in misalignments and torsion across to the wind turbine. This could be resolved by moving or rearranging to a stern-mounted gangway. And here the roll motions are compensated by tilting the platform itself. And you also have a pedestal that is dynamically compensated. This also allows us to distribute the overall height differences based on motions of the vessel over an extended length, which also resolves the more and more commonly faced limits, being inclination of the gangway. Often end clients impose restrictions on the permitted inclination. This solves that. Importantly also, operating from the stern provides a weather vaning flexibility, as shown here on the illustrations to the right. The vessel can be connected, but have a large degree of freedom in terms of weather vaning as per weather and current. Given the improved maneuvering capabilities of the double-ended design, we are currently in the process of exploring and establishing improved ways of maneuvering that will have an effect on how DP systems are configured, and which would also depend on creating new ways of acceptance to how you can operate in a wind farm, new types of safety barriers allowing for more effective and straight-on type operation. But for sure, the double-ended design provides very interesting opportunities in our view. But as mentioned, we do have available the option of a midship-mounted gangway, which has also benefits in terms of workability, possibly. The boat transfer system is an interesting solution to improve the safety and robustness of daughtercraft operations, which especially for a larger SOV with more technicians and where it will be more dependent on daughtercraft is important. The boat transfer system is basically a semi-submersible cradle where you can lift the daughtercraft in and out of the water. It allows for controlled launch and recovery. It prevents the need to operate painter lines and do hookup of davits. It allows for inboard boarding and disembarking, especially in inclement weather, rather than doing it via a boat landing. And not least, it provides for more reliable performance. And that reliability is what in practice determines the weather window that you can operate in. Here shown in the inboard position where you can do embarking and disembarking of the vessel. It is then moved over the side and lowered along rails into the water from which the daughtercraft can propel itself in and out. Meaning that this operation can take place with technicians and crew of the daughtercraft being safely housed within the vessel. So the main benefits then being that you have no pendulum effect due to long wire lengths. You avoid the hazards of painter line handling and hookup. Especially hookup is dangerous in the case of dual hook larger daughtercraft, where you need to hook up also typically on the bow. So overall, this is a much safer means of operation. In terms of power systems, we have opted for a battery-biased system. That is with the idea that all infield operations can be done electrically. The baseline case is based on a daytime operation, 16 hours of operation, leaving 6 hours of charging a night and 2 hours idle as a buffer. We have also installed diesel gensets, which allows for flexibility to operate also in areas where you do not have access to offshore charging, and as a range extender, typically used in transit to and from the field. The propulsion setup in the vessel will typically consume 500 to 1500 kilowatts for propulsion power during infield operation, with occasional peaks up to 2500 kilowatts. The installed power is higher for sure, also due to redundancy. And in inclement weather, power peaks also above 2500 kilowatts may be occurring. In transits, depending on the speed, you can use anything between 1000 and 3000 kilowatts, roughly speaking. Importantly, though, is that average infield propulsion power used is less than 1000 kilowatts. And this is what makes batteries viable, because the actual energy flows are not substantial on average. And at the same time, batteries are capable to handle substantial power dynamics, as we see from the figures above that you have. That means that power generation can be configured according to more the average power demand rather than the peaks. And reducing the power generation demand will also greatly facilitate the use of future fuels. Although we have opted for electrical operation with offshore charging as maybe the more viable avenue, other fuels can be considered. But typically when you use future fuels, you would want to minimize the power generators. And for instance, if you use fuel cells, they are not particularly capable for handling power dynamics. So the combination with a battery-biased system is ideal. We have considered both DC and AC systems, done fairly comprehensive analysis based on 2-split and 4-split configurations. For the given operating profile we had here, and in the case that we do assume diesel generators and as the power generator, meaning we do not consider offshore charging, the DC closed ring proved to be more effective, but this is very case dependent. At the same time, the DC closed ring setup is very suitable for offshore charging. So this vessel can easily incorporate offshore charging to the energy mix. As mentioned, the idea is then all electrical infield operation with overnight charging. If you have a 24-hour operation, you will typically split the charging maybe into 2 briefer periods. Obviously, that would then depend on a higher power charging to sustain the required energy transfer. We are working on relevant solutions for offshore charging. The buoy indicated here is just as an illustration, so don't construe that as being our proposal, but the principle is indicated. And then overnight, typically charging while being moored to a buoy, maybe having one thruster in operation for heading control and ensuring gap versus the infrastructure you charge from. And in the event that batteries are depleted, you can start up the diesel generators and support during operation. Then I will pass the floor to Odd on some of the risk implications of offshore charging.
Yeah, thank you, and good morning to all. DNV's role in this NEXUS project, a part of it at least, was to check and verify whether current regulations are challenged or whether there are no regulations in place or do not fully cover the intended application. So charging of batteries in port is already well proven, and there are several technical solutions in place. But and the charging of batteries at the wind farm was also early identified as an obvious way to reduce emission. But at the same time, moving from port and to the exposed maybe areas of the wind farms we are entering into new areas. So it is also important that we need to consider the charging unit and SOE in common as a shared with the shared interdependencies. And the charging unit, as shown here, was a floating type, but it can also be a fixed structure to the seabed. So we carried out HACID in the NEXUS project based on a floating charging unit and where the charging cable is brought on board to the SOE. We then identified the hazards covering also disconnections, and we carried out the risk ranking based on that, which was based on the IMO FSA guidelines. And we have mentioned or listed some of the hazards that we considered with the highest risk ranking here. Collisions, contact between the vessel and the charging unit upon approach, loss of positions, DP failure, for example, impact to personnel during connection, water in connection, plug socket on board that is identified as the highest risk, at least for this concept. Cable can be dropped into water or on deck. We have a possibility for incorrect energizing of the system and live connection during accidental disconnection or loss of position. Next slide, please. So there are, for shore power, there are already well-established regulations. We have mentioned the DNV class notation shore power. But there is also the international shore power standard for utility connections in port for high voltage connections. If these regulations then are expanded also to cover the offshore charging, we have some recommendations, among other things, which need to be considered in addition. The shore side need to be considered, and by the shore side here is of course intended to mention the charging unit. We need to have mechanical emergency disconnections of the cable plug in case there is a drift off or loss of power or failure of the cable management system. We need coordinated protection of the whole installations, including protection against lightning strikes, and mechanical protection of the cable between the ship and the charging unit. It could be subject to damages caused by other ships or daughter craft, for example. And then there will be necessary to include a number of operational requirements covering the whole process of connection, disconnections, and staying connected. So thank you. That was a brief summary of the hazard. So Luis, will you continue?
Thanks, Odd. This is Luis Mourelle from GONDAN Shipyard, and during the duration of NEXUS, our main task was to provide evaluation and validation of the concept developed by Kongsberg from the construction point of view. This evaluation was done based on our experience building several SOVs currently in operation in the North Sea, including the two reference vessels, Edda Passat and Edda Mistral. And our assessment is that the concept developed during the project is definitely feasible, realistic and buildable. The symmetry can provide some minor advantages, such as simplified accommodation layout, more room for reusing engineering, or increased number of repeated tasks during the construction. But perhaps the most remarkable advantage is of this design is its modular approach and its scalable approach. Our experience on this market is that the standard procurement model being carried by wind farm operators consists on calling for tenders for long-term charter of site-specific SOV designs. The time between the call for tender and the expected delivery are very tight, and sometimes a front runner is necessary, which increases the cost of the operation for service providers. If a design could be modular and scalable enough that allows the reuse of a significant amount of engineering from tender to tender, this will significantly reduce construction time from contract coming into force, which has a huge impact on the competitiveness of a ship owner's proposal. Regarding CapEx, compared to conventional designs on the market or currently under construction, CapEx of this design is higher. This is caused mainly by the concept of operating in fully electrical mode, which demands a very significant number of batteries on board that has an impact on price. That being said, the cost of batteries must be evaluated by wind farm operators, considering the overall fuel savings during the whole 10 to 15 years operation of such vessel. Other causes for cost increase are the innovative mission-specific equipment, such as the boat transfer system or the configuration of the gangway, but those are truly add-ons on the design, so to speak, so they must be evaluated considering aspects such as reliability or against potential reductions of LTIs on site, but they are not fundamental to the design and could be added or removed according to the specifications. So that was the evaluation from the shipyard point of view. In the end, feasible and advantageous symmetric design, higher CapEx, but needs to have a holistic view on the whole cost of the project. And that's it from my side.
Thank you. Then I believe we pass the floor back to David.
Hello. Yes. Hi. Thanks, Vidar. Thanks very much for that, Vidar, Lewis, and Odd. We were going to hold a little coffee break now, but we're running a little bit late. But we have had some questions that have come in, and I think what I'd like to do is to try to take these now. People can go and obviously have a coffee if that's possible while we're answering them. I think we had Fernando's, I think, given us a number of questions, actually. Thanks, Fernando. I think the first one was for the presentation from Iraklis and Makis, and then we had some that were for Leslie's team. Have we got capability of answering those? Does anyone want to have a look at those questions at all?
Yeah, actually, thanks, Dave. If I try to answer the first question, first of Fernando's question on the fuel consumption, if I may. So the question is about what percentage of fuel consumption was possible with a daily schedule planner, as in what range was possible, from 5 to 10% or more. So if I understand the question well, this is related to comparing the operational planner optimized scheduling and minimized the fuel consumption compared to an actual scenario that has happened, that actually took place. Again, if my understanding is good. And now, in this respect, we didn't have that capability to compare the results of the planner and the different scenarios, compare them to an actual case that actually took place within the wind farm. The operational planner, however, provided, what I presented was to provide a picture of how adaptable and how customizable this tool can be in order to accommodate different vessel combinations or different inputs or different locations, let's say starting locations for the SOV. So it doesn't have to be the hub port, it can be like a standby location close to the wind farm. That's the same for the CTVs or the daughter crafts, etc. Which will minimize also the fuel consumption, will improve also the availability, the overall availability in the operational window for maintaining a number of wind turbines on the same day. However, it could be interesting, and that's what we are considering next, to have this type of validation, actual validation with an actual case study, having data coming in from an actual wind farm on a, let's say, particular specific route that an SOV or a CTV or daughter craft has undertaken, and compare these results of the actual case with the operational planner as well. And that can be done either through an actual case or through also having a comparison between different tools, a benchmark study, having the same input and trying our tool and another software tool as well to see what are the results. In this case, I hope I have answered your question.
This is Fernando. Thank you very much, Iraklis. So yeah, I was mentioning more than for what do you call, not against an actual operational data, but just from your results, because you presented one study case with this fuel consumption, the other one which a different route with a different fuel consumption. So from those differences, I just was trying to get a range of what actual fuel consumptions you could reduce in range. So did you see that a change in route could change your fuel consumption by 50%, or were most of them changes around 5-10%, like small cost reductions in the different routing and the different scheduling?
Yeah, I see your point now. Thanks for that clarification. Actually, the scenarios themselves are not comparable as such, as they consider, for example, a different set of failed turbines or turbines that need maintenance. So we cannot directly compare the use of the SOV or the combination of SOV and CTV or CTVs only, as in these scenarios presented, they do not serve, or they are not used to maintain exactly the same number of turbines. And that's because we want to provide as a broad spectrum of case studies as possible. However, having said that, that's something that we can actually do. We can perform for exactly the same number of turbines to be serviced and exactly the same conditions, like stay close to the turbine or stay at the standby location, a bit off the wind farm, etc., etc. Try to use a number of different vessels, either an SOV or a CTVs only, or a combination of SOV and CTVs, etc., and compare then the fuel consumption and the time it takes to service all these turbines, etc.
Yeah. So I was talking about the exactly same scenario, but just different routing and different scheduling. That's where I would see like the interesting part of seeing how much you can reduce fuel consumption when you know you have to service the same turbines, the same conditions, but you just do a different route and you assess it with the tool. Yeah, thanks for that. No, we haven't done it in this work, but this can be easily done since the tool can accommodate these scenarios as well. So thanks for the recommendation. Actually, it's something that we can try very soon. Actually, yeah, try to incorporate it. Thank you.
Thanks, thanks, Iraklis. Well, we got we've got a little bit of a couple of minutes now before we start again. I think Matthew and Martin, the other questions, have we got a chance to answer any of those at all in this short session?
Do you want me to answer? Hi, it's Leslie here. Quickly answer the ones about the second presentation. I can at least give a short answer and Vidar can add in more details. But I think from a modelling point of view, there was a question asked about the breakdown of operational costs. So from a modelling point of view, what we were effectively doing was building on the diagram that Ewan showed about the utilisation of the vessel. And there are different costs associated with each of these activities. So we're basically building up operational costs from that basis. But that built into other costing that Vidar did, so he could explain a little bit more. And
yes.
I'll let you carry on, Vidar.
Each concept was created with its own cost structure. Of course, this is one example from a medium-sized SOV, a generic example. And of course, this means basically 10% fuel, 50% OPEX, including the marine crew and the technical maintenance, and equivalent of 40% of CapEx. Of course, we do have a breakdown of the individual components, but I say that is a bit internal to us, and it will also depend very much on the charterer's choice with respect to crewing and operating model. But each concept has their own breakdown. Then I can maybe also address some of the other questions a bit quickly. Questioning about why whether we have considered vessels more than 60 technicians. Yes, we have, let's say, kept that in mind. At the same time, when we become above 60 technicians, you become prone to bottlenecks, such as a gangway, when the autocrafts cannot be operational. So there is increasingly penalties of scale. But the ISPOC model is a tool exactly for assessing that. At the same time, we see that a larger SOV will actually be capable to service wind farms typically larger than the current scale. So it's also a question about the industry catching up in terms of wind farm scale. But it's definitely a very interesting topic that we are looking at, and ISPOC is an important tool to resolve it. Some question about autocrafts with 1.8 and 2 meter transfer capabilities. Yes, that is fairly optimistic, but the point of assessing it is to see what if. So we don't claim that these are existing. We are rather telling what if they did exist, although there are some concepts moving towards that. Then there is a question regarding whether we see hoisting with the gangway as a requirement for the operation. I understand that as then using the gangway as a crane. We have not particularly considered it, but in my view, it's an interesting prospect, and we do consider that fairly as an integral part of new designs that we are proposing. Let me see. There is also a later question for me about the charging time, 6 to 8 hours. One of the main ways to improve productivities and economies of scale is obviously 24-hour operation. So we happen in the baseline case to have 6 to 8 hours available during night, which allows for a very cost-effective implementation of batteries. At the same time, for overall cost efficiency, 24-hour operation will be better, and probably also putting the additional money into allowing for briefer charging periods, for instance, 2 times 2 hours during a 24-hour period. Then you need to invest more in the infrastructure and the vessel systems. In terms of how to connect to the charging buoy, we are working on such topics. I think it's a bit premature to reveal our thoughts on that, but we are certainly keen to discuss that prospect with operators of vessels. Then maybe David would comment on whether we have consulted with wind farm operators for benchmarking.
We did actually have an operator in the project initially, Park Wind. They didn't continue. I think the process we've set, and someone can support me on this. I think that the process we've actually Martin and etc. can perhaps help in the process we put together the project. We did actually take into account what we believe to be the right requirements, but we have not, I don't think, actually had specifically an offshore wind farm operator directly involved. Do you want to say anything, Martin, about? We've certainly had a few conversations. Anyone to support?
We of course established a reference group. We had several discussions within the project with a number of these operators, where we try to gather as much information as possible. But it is challenging, of course, because each operator works in a different way. They're competing against each other as well. So getting the correct values on the table is challenging, and that's why everything we do is also a little bit more relative to each other rather than its absolute values. I think that we should keep in mind as well.
Yes.
While I'm commenting a little bit on the offshore charging and the logistics of that, Peter is correct. That will require a close cooperation between how the wind farm is being run and how often you want to charge, and the sizing of the battery pack and the power of the charging itself. So there is a lot of parameters that are involved in doing offshore charging.
Yeah, I think you're going back to the benchmarks, the operating benchmark. I think you're right, Martin. We did say that there was a danger that if we did follow one path, that we would not look at the overall scene. And so I think we missed the wind farm operator, but at the same time, I think we got more value out of a wider sort of view.
Yeah, and I can add to that also that I think one of the very important outcomes of this project is that we have established a framework enabling us to assess considerations that are vital to operators. So I think with that framework, it will also be more relevant to now take up that discussion with operators, whereas operators tend to be a little bit secretive if we cannot add value to the discussion. But with these findings, we can add more value to that discussion and hopefully create a more open dialogue with selected operators.
Right, I think we have to move on now. So the next session we have here, because we've missed the coffee break, hopefully people can catch up on that coffee breaks. But we now pass to the business case and scenario planning, which I think Ian, was it Matthew or Ian going to lead this one? Was it Ian?
Matthew's going to start off and then.
Oh, Matthew's going to start, is he? Okay, right.
Yeah, so can I, Vidar, can you stop sharing if that is possible, Vidar? Thanks, and I'll take control. Thank you. So hopefully everybody can now see the full screen. If not, somebody can shout out. So in this final section, we're going to look and to bring together a lot of the modelling that's gone on to date, and look to the future as to how these vessels might be used, and really try to revisit some of the connections that we made, what Leslie brought up earlier on, between the operational performance of these concepts and the business value that they can deliver. It's going to be myself. So my name is Matthew Reevy from the University of Strathclyde Business School. I'm joined by Ian Belton. But as with all the work that's been done within this section, it's really been a team effort from myself, Ian, Ewan Barlow and Leslie Walls that you heard from earlier, and John Quigley at Strathclyde University. So Ian will talk a little bit about the foresighting that we did to think through some scenarios. And then I'll talk a little bit about some of the modelling that we did, some modelling that was focused very much on the vessel owner to help them develop a business case. And then the scenario-informed analysis that we used around the logistical concepts that Vidar and Leslie and Ewan spoke about earlier on. It's probably worthwhile reflecting a little bit upon the rationale of the approach that we're taking here. So rather than considering the business case in quite a narrow sense, as just incoming and outgoing, we're taking a much broader view of a business case as to be a much more general, holistic strategy as to how we develop and finance vessels that are financially viable over its lifetime. And this part about over its lifetime, I think, is quite an important part, because as Leslie mentioned, we're dealing with vessels that are going to be operating on wind farms that have not been built, and in some cases may have not been designed. So it's really important that we think through not just over the next sort of 5-10 years, but over the entire lifetime of the vessel. What's the different scenarios that it could be faced with? For here, we're going to try to integrate some of the output of the ISPOC model that was developed, and we're going to also develop some scenarios through scenario planning to develop a business case model that can be used by vessel owners, but can also be used by the other stakeholders. Here, when I pass over to Ian, he will explain how those future scenarios were created and developed, and to provide at least sort of indicative prototype futures and scenarios. And then finally, I'll come back to me. I'll talk about how we extended the ISPOC model and how we developed a Monte Carlo simulation model to capture uncertainty that's been particularly informed by the ISPOC model. So why don't I hand over to you now, Ian? And if you want me to walk through these slides for you, just say next and I'll flick through.
Sure, thanks, Matthew. I will see if I can take control. If I can.
So I've given you control now.
Okay, thank you. I think it's going to be best if you keep control, actually, Matthew, if that's all right.
Okay.
It's going to work better. Great. So yeah, the first question is, I suppose, why did we develop foresighting scenarios? How does that fit into the overall NEXUS project? And you can think of it as the outer ring of the modelling framework that Leslie presented earlier. So the wider business environment that impacts the decisions that have to be made when designing an SOV. And obviously, offshore wind it's a rapidly evolving industry, and predicting how it may develop in the longer term, particularly beyond 10 to 15 years, is pretty challenging. It involves dealing with a great deal of uncertainty. And also, SOV design requires a long-term perspective, given the large upfront costs involved and the long 20+ year working life of a vessel. So we wanted to think, we're thinking far into the future, and we wanted to think beyond just extrapolating from a business as usual, plus or minus a bit, and explore more extreme but possible and plausible alternative futures that a vessel might have to operate in. And the aim of this kind of scenario-based foresighting is to generate that broader perspective, as you see from the visual I've got here, to widen the exploration of how different variables, the values of different variables might change, so that we're thinking about a bigger future space. And in that way, we can examine the robustness of any particular vessel concept to a wide range of contrasting future environments. And while this kind of scenario approach, it provides less depth than conventional sensitivity analysis for individual variables, it's a really useful way of investigating this kind of complex environment where there's a large degree of dependency between variables. Could I have the next slide, Matthew? Thank you. So how did we go about making these scenarios? Well, the method we used is scenario planning, and specifically what's called the intuitive logics method. It involves a 2-day workshop. In this case, we had 19 participants from different stakeholders in offshore wind, and I should mention 3 of them were actually from wind farm operators. So they were represented in this, in terms of engagement, they were represented in this process. And the way the process works is the group starts by brainstorming. This is why you see a picture with all those post-its, brainstorming every possible driving force that could impact offshore wind over the next 10, 20, 30 years. You then take those driving forces and you make them into clusters of related items. This is the second graphic. They become directed influence diagrams showing cause-effect relationships between those forces. Then after that, you identify which clusters are believed to be highest impact on the future of offshore wind and also most uncertain. And in this case, we had 2, one that was about forces that would affect the strength of support for expansion of offshore wind and therefore speed of installation of new farms. And the other force we had was extent of focus on technological innovation versus standardization of existing technology. So once you've got these 2 uncertainties, you develop alternative outcomes for each one, extreme outcomes, broadly speaking, high or low. For example, a future where the focus is on innovation and a future where the focus is more on standardization and optimization. And then you cross the outcomes. That's what these little diagram shows. You cross the outcomes and you end up with 4 frameworks for scenarios. And then finally, once you've got these 4 scenarios, you develop each one, you map out the pathways to that scenario's endpoint in 20 or 30 years' time, and you agree an overarching narrative. Could I have the next slide, Matthew? Thank you. So what scenarios did we create? Well, I don't have time today to go into detail about the scenarios, but you can see they're on this axis of standardization versus innovation and more or less push towards supporting offshore wind. And we had 2 relatively optimistic scenarios. We have conservative success and bigger is better. Conservative success being more about focus on scale, number and size of wind farms, steady growth in turbine size, progress on standardization and a shift towards planned maintenance away from unplanned to some extent. Bigger is better is more about innovation, driving turbine size up, perhaps as far as 20 megawatts and beyond, less of an emphasis on standardization, optimization, perhaps more maintenance required in this scenario because of the new technologies and which might be more uncertain and perhaps less reliable in the short to medium term. So those are the 2 optimistic ones where there's where the flow of investment and support for offshore wind continues. Then we have 2 more pessimistic scenarios where things perhaps don't go as smoothly as the market now anticipates. In one, the focus is in one pure cost. The focus is very much on offshore wind competing on the basis of costs, so bringing down O&M costs, focusing on tried and tested technology and standardization and reducing maintenance overall. In the other one, survival of the fittest, perhaps the most pessimistic if the market is tougher for one or other reason, perhaps to do with other competing energy sources. This is a very uncertain scenario where perhaps it might be necessary to innovate in order to try and survive. And so in this case, maintenance requirements might be quite similar to scenario 1 actually, but with a different profile. So those are our 4 scenarios. Matthew, could I have the next slide, please? So the next challenge is, how do we take these scenarios and translate them for use with the iSpot model so that we can learn, so we can explore these issues around robustness to different futures? The challenge being that scenario outputs are qualitative, they're narratives, they're influence diagrams, while iSpot requires quantitative input values. So somehow or other, we have to move from one to the other. Given the lack of, generally speaking, lack of publicly available data on a lot of the variables we're interested in, we decided to use expert judgment. We identified a small group of subject matter experts, and we also, obviously, we know the inputs that iSpot requires. We started with a group session where we worked on identifying the iSpot inputs that are likely to differ across our scenarios and likely to affect the KPIs that we can model. And we also agreed as best we could how those key inputs might differ across our scenarios. And at this stage, it was primarily directional. So do we think this will go up or down, or larger or smaller? Although we did do some estimation. Then after the group session, we had individual follow-up sessions where the experts estimated the percentage change from our baseline input values. And we facilitated as best we could to get the experts thinking about the dependencies between variables. And at the end of this process, we had four snapshots of input values that we think are appropriate for each scenario. And now I'll hand back to Matthew, who will talk a bit more about what we did next.
Perfect. Thank you so much, Ian.
Thank you.
So what I'm going to do is walk through how we utilise some of that output to do modelling that we hope can be useful for different stakeholders, but in particular for the vessel owner to make the business case. So first we'll start with the business case model for the vessel owner. This was informed by collaboration with GMSL. So 4 key aspects of the business case that they felt there was. There's the income and revenue that is generated over a 10-year period with the vessel. There's the OPEX over that same 10-year period. There's the CAPEX, which is all the costs that are incurred in year 0. And then there's this concept of the residual value. So the residual value is the estimated value of the vessel at the end of 10 years. 10 years was chosen because that is the typical charter length and contracting length for one of these sorts of vessels. And then what we estimated was the residual value as a percentage of the CAPEX costs. On the right-hand side here, you can see a table that shows you the different incomes that are considered, the different OPEX that are considered, and the different CAPEX costs that are considered with the residual value at the bottom. And for each of these variables, we elicited from experts a minimum value that they expected it to be, a most likely value that they expected it to be, and then a maximum value. And then we developed a Monte Carlo simulation that could allow us to identify different KPIs that the vessel owner was interested in to assess what's the potential range of values for this particular KPI. We're going to focus, just for the purposes of this session, on the internal rate of return. Again, we could have looked at a variety of different KPIs, but this is the one that we've decided to focus on. So in terms of as a base case for some indicative values, and it's not to say that this is indicative of the concept, but indicative of the approach that we can take. So this is just illustrative. We can create a baseline case showing the uncertainty for the internal rate of return for a particular vessel. Here showing that for this particular vessel, the range of potential values really moves from 0% all the way up to about 23%, with a sort of a peak around about 12 or 13%. That is useful potentially on its own, but then we might want to compare it to a different vessel. So here we're comparing it to an alternative vessel where the most likely value for the day rate is likely to be higher, but here we're capturing that there's more spread on that. So here we can see that there's a slightly higher upper side benefit on the alternative vessel, but you can also see on the left-hand side that we're absorbing a lot of risk. Moving through this quite quickly, we can also do this for other variables, such as, in this case, inflation. So here we can see what happens when we have a case of high inflation or low inflation compared to the baseline case. And I'll move on to the last one, because the last one illustrates how we were using the scenarios. So here we were using the scenarios to really think about how the residual value of the vessel might change. So in this scenario where everything is driven by cost, then that particular vessel might not be, it might not have a very high residual value, here represented by green. In another case, it could be that the SOV is very much in demand for a number of different reasons. And in the sort of purple line, you can see the upper end value that the vessel could get under that scenario. And again, the blue being the baseline case. So that's indicative of some of the analysis that we can do with the model that we developed for the vessel owner. Next, if I come on to very quickly move through how we can use ISPOC within the scenarios. So here there's quite a lot on the screen, so I'll talk through it. At the top, we have got the total cost KPI, and then the sub costs to that, the TOTEX, the unrequired technician costs, and the loss generation. Note that the TOTEX costs combines the CAPEX, the OPEX, and the scenario-specific VOIEX costs. For each KPI, we're considering 4 different logistical concepts indicated by different colours, and then the 4 different columns are the 4 different scenarios, all measured on the same scale, so we can see across which scenarios most divergence occurs. Again, there's quite a lot that we can go through here. I'll go through it quite quickly because there's another slide that I also want to share. Here we can see that the best performing logistical concept varies between the large, which is the purple, and the medium, which is the blue, for scenarios 1, 2, and 4, with no difference from this CTV on scenario 3. So you can see in scenario 3, they all come together. The large monohull produces a sort of consistent relative value throughout, indicating that the costs are consistently balanced by the vessel activity, while the relative costs of the small monohull SOV and the CTV vary quite significantly between the scenarios, indicating that the effectiveness of these concepts is far more depending on the scenarios and the operating environment as compared to the large monohull, which is a little more robust. Finally, in terms of the sort of output that we've looked at, here we're looking at more sort of conventional sensitivity analysis, where we're looking at the effect on productivity, depending on the number of turbines on a farm and the size of the vessel, i.e. the number of technicians that we've got in it. And we're comparing 2 scenarios here, conservative success and survival of the fittest, just for illustrative means. Deep red means that the vessel is more, sorry, the turbine, the farm is more productive, and blue means that it's less productive. Here we can see that for the large monohull, it's fairly robust against changes in the number of turbines and the number of technicians. Here we can see that CTV only, again, is slightly changing as you increase the number of turbines. And similarly, as you go from medium to small, the robustness decreases. Over in the scenario 4, between the 2 scenarios, where there's a shift in the degree of innovation and hence increased uncertainty on the reliability of the turbines, you can see that the productivity, even with the large monohull, starts to drop slightly as we increase the number of turbines. But you can see that that effect is much more pronounced as you go smaller and smaller and smaller. So here it allows us to assess the robustness of those different vessels, and this analysis allows us to think about the capacity matching between the logistical concept and also the technician capacity when we want to tailor it to wind farms of varying size. So if we think about it, and this is my final slide, if we think about it as a more high level approach, what have we tried to do here? Well, on the bottom left in green, we've identified our scenarios through our foresighting process, and we've used that to inform the business case modelling, which in turn helps to inform the vessel owner. And then within ISPOC, we've been able to use the scenarios to further expand and broaden the analysis that we've done with the ISPOC model to really look at vessel costs and particular KPIs more broadly. So I am wary of the time and the fact that we want to get to a Q&A session both for this part and more broadly. So why don't I open it up to any questions that have came through, or I can pass back to Dave if you want to go to a more broader set of discussion and questions. But thank you.
Thanks, Matthew. I don't think there's any further questions come in, actually. We think we answered the previous ones. So what I'd like to do is to perhaps move to... So first of all, I'd like to thank all the presenters. It was really excellent, I thought, that the webinar. So thank you very much. But I'd like to move now to really what we call the panel session. What we're trying to do here is the project has a couple of topics, 2 topics particularly. And really, we'd like to start some discussions around those with a panel. So we have the panel there shown. We have Fernando Sevilla. Thank you, Fernando, for offering to join. So Senior Offshore and Wind Engineer for DNV. Got Martin de Jong, who's actually the Chief Designer for Kongsberg, who's actually on the project, but he's obviously got very good background. Martin Dry, who's the Director of Engineering for Global Marine Systems Limited. And thank you, David, for offering as well to come into the panel, Maritime Decarbonisation and Offshore Renewables Energy Catapult. So we did have, hopefully, I think the panel's been asked the questions and some of the context around the topics. But I'd just like to start off with the sort of, as a broad thing, the outlook for the SOV size, scale of wind farms and turbine capacity. So this is a relatively sort of open, a sort of a relaxed conversation. I don't want to sort of point questions to people. And if anyone from outside of the team has got questions, perhaps again they can put it on the chat, and we can either answer it now or answer it afterwards. Okay. Does anyone want to start off? Fernando, have you got any comments about the first topic?
Hi, everyone. Yeah, thank you very much. Yeah, so the first topic related to the pros and cons of larger SOVs and associated transfers, right?
Yes. Yep.
Yeah. Yeah, this is a very interesting one. I was going to ask a question from the presentation because there was already there in the last slides a total number of turbines, for example, that was considered for the last slide, going to like 289 turbines. It's right now very interesting to think about what SOVs can actually do. We have projects already operational that started using SOVs with 150 turbines, for example, in the Gemini project. We have the particular case where there's 231 turbines, different models, 4 different projects in Germany operated with an SOV. And that's already like showing the high capabilities of SOVs in the operations of wind farms. So that's what one of my questions was gonna be, if detailed assessment has been done on this, on what is the actual number of turbines that could be considered to be possibly serviced by an SOV. By going larger SOVs, we're talking about, and that's also related with my question of if higher than 60 technicians SOVs have been considered. The pros that I see on a larger SOV would be, obviously, you have higher capacity of technicians, therefore you can probably be able to, well, logically you're able to service more turbines. Obviously there are bottlenecks. The bottleneck would be that you still need to transit to the turbines, you still need to have time to transfer the technicians and the equipment. And for that reason, there could be there will be for sure an optimal or a limit on how many you can do. the way of sorting this out or doing or being more effective for an SOV that has larger capacity will likely be that with more daughter crafts or with more support CTVs, you will be able to certainly deploy a wider amount of technicians, and therefore you will be able to even source, as we're seeing, more number of projects, even not only one big project, but a different amount of projects in the vicinity. The cons of going larger that I think of is that because of this higher number of technicians and higher number of transfers that you need to do, you will likely be reliant on the capabilities of the daughter crafts and the CTVs, and then you lose the accessibility, the improved accessibility that an SOV and the gangway gives you. So in some cases, and what we're starting to look is that projects that are going to be that are further away from shore and that are large number of turbines or clusters of projects that are far away from shore, they will certainly have to use an SOV, and probably the cost will be more optimal when you have one SOV that its main benefit is just going to be to reduce the transit time, but the operations will still be the same or similar to having a CTV strategy. The benefit that I could see there is that the SOV, as it stays at site, is reducing the transit times, and therefore the main benefit of it is that you move your O&M base from a port to the site. Those are just some of my thoughts on these pros and cons of going larger.
I can maybe add a couple of things here, because as I was also part of this project, one of the concepts was a non-direct transfer SOV, which basically, as Stan describes, is providing a platform offshore and do the distribution with smaller boats. But then you still have that asset available, for example, to do lifting operations, because that's one of the drawbacks, of course, if you only do the transfer with CTVs or daughter crafts, is that you're missing crane capability. So having an asset there that actually can move around, rather than for what we also had is the flotel, which is fixed in location. You actually have an asset that has lifting capability, and also a gangway, of course, in order to supplement the transfers. So that was definitely one of the ways of looking at it. It's an interesting question with regard to what happens if the vessel gets bigger and bigger. The operation speed, for example, does risk increase with regard to collision with the turbine. Smaller vessels, more maneuverable vessels. We have, of course, also a drawback that we need to have more and more power requirement, bigger vessels. DP capability needs to, of course, be the same. So you need a lot more power in order to maintain the capability. So there are some plus and minuses, I think, with regard to really going much larger than 60 technicians in that sense. But it all has to do with, as you say, also asset sharing between sites, campaign-based maintenance. What do you do with the planned maintenance and unplanned maintenance? Is that scheduled? Is that unscheduled? Can you schedule so that you only sail short distances between the turbines to reduce the sailing time in the field? I think that was also what the challenge was in this project. There are so many factors that determine in the end, what an optimum solution could be. I know, Martin, maybe you have some to add.
Yes, good morning or good afternoon, everybody. First, I'd like to thank Arctic and the NEXUS team for an excellent presentation. I am aware of all the work and the commitment that has been involved to deliver this project, and I'd like to say it's really appreciated by those of us who have seen this presentation and can see the level of work that you put into it. So that is very much appreciated. The project demonstrates, I think, that there isn't a one design fits all for wind farms in the future, and the focus that you've put on what I call technician efficiency and the operational scenarios that optimize this are key to a successful vessel. When looking at the first topic that you've come up with, which is the size of vessels and the scale of wind farms and turbine capacity, I think the good thing about this project is that it addresses that, and you've got a model now that can assess specific wind farms and come up with really bespoke solutions. In terms of vessel size, I think that depending on the size of the wind farm and depending on the size of future turbines, I think there is a scenario where larger SOVs would be viable. My understanding is that as turbines get bigger, the teams that will go on board those turbines will be larger, but the number of visits that that the operators or the owners and developers are trying to create is to reduce the total number of visits. So I can see a situation where there will be more technicians, where you might go from a 4 or 6 man team up to a 12-man team for some of the larger turbines, which would require a larger number of bodies on board. But the actual number of visits may not increase significantly. And I think that is something that the scalability of this design will easily be able to compensate. It's about the number of drops per year, and I think that any SOV in field is limited to the number of drops that it can do when it's running in field, going from turbine to turbine, and you look at the length of time that those technicians are on board the turbines, you're in a situation where that one vessel can only do so much in the day. So I think I agree with the team that the addition of daughter craft and potentially for the larger wind farms, the integration of CTVs to complement the SOV will make it expandable. And I do see that as the bigger wind farms come into play, there will be, I think, a trend for the SOVs to get larger. I don't see them the trend really for a smaller CTV, because I think you've proven in this analysis that because we require a certain amount of steel, a certain amount of thrusters, a certain amount of accommodation and a certain type of equipment, a crane, the cost benefits of going smaller with less people isn't really there. So I think you've hit that sweet spot in terms of the design and the fact that you can make it expandable to suit specific wind farms. So that's where I see in terms of scalability. We have seen a number of wind farm owners combining wind farms into maintenance scenarios. So already we're seeing situations where SOV contracts are looking at 2 or 3 wind farms, and then maybe moving an SOV that can do specific activities from wind farm to wind farm, and then shuffling CTVs for other activities that are simpler. And I think Martin's been quite clever in identifying the ability to lift heavy items on board is key to that. So you can, in your planned maintenance, I can see that developers will go to that more organised scenario. And again, the great thing about this analysis is that you can pull together these wider issues and come up with a well-engineered and well thought out solution that delivers technician efficiency, not just an efficient vessel. Thank you.
If I might say something just quickly, just picking up something on what Martin said there, which I think was very interesting, is that we're not just looking at wind farms, because quite often they're, looking at these sort of very large 1 gigawatt plus capacity wind farms, but clusters of wind farms formed together. If you look at a lot of the recent bidding, certainly in the UK, the recent Crown Estate bidding, you were looking at owner operators trying to get wind farms that were near to their original sites. And I'd imagine that a large part of that will be the operations and maintenance, looking at the whole cluster itself as one operations and maintenance areas, whereby for the more specialist tasks, although you may look to have an SOV on each wind farm, you would only look to put the very specialist components on possibly one vessel, so you can save maintenance costs there. What I think will be very interesting is there are some large areas which haven't been taken just by one owner operator. So for instance, Dogger Bank looks like it's going to have, well, it is going to have more than one owner operator. Will you see joint maintenance contracts? Obviously they'll look to have their own capability, but where vessel operations are quite specialist, will they look to have collaboration between them, or will they look just for their own operations? I think if there is collaboration, there's probably some cost savings available.
Thanks very much. That was anything else at all on this particular topic? I think that was really useful, actually, sort of discussion.
I think maybe one short comment, David. There is this comment on using drones for certain activities, and that is definitely something that is taken into consideration. The question, of course, the size of the drones and what type of activities. But yes, I think absolutely an SOV should be able to function as a base for drone activities.
Yes.
That becomes part of the planned maintenance and unplanned maintenance.
Mm-hmm. And we talked about this. I think we talked about CTV and SOV here, but operations near shore. So do you want to say anything about that at all? There's another comment.
Yeah, maybe Martin, you're the best one to answer that one, but we do see a shift, of course, offshore, and that's more the area for an SOV. The short distance to shore is definitely more CTV type operation. But yeah.
Okay.
That's what I see so far, at least.
I think it's quite simply there that the amount of time that you spend in transit has an impact, and then therefore the SOVs become much more effective. I think that's a pretty well-known fact. I mean, in our business, one of our business sea wins, we've just released a very fast CTV, which helps to address that. It can do 40+ knots, but it doesn't get to the long-term solution of the larger wind farms. I think that's definitely SOV based, and some people are still considering maintenance islands for the very big wind farms. What's interesting here is the questions that they are asking about scale, size, and the wider picture could be answered with this very thorough type of analysis that the NEXUS project has gone through.
And also, just to add on that, also from experience, we know that there are operators already looking into clustering their already CTV strategies with projects with SOVs. So definitely we see that coming a little bit more, but difficult to say if it will be a trend and it will happen a lot, because also projects that are still quite close to the port and have benign conditions are probably still be more optimal to be just run with CTVs. But obviously it's going to be more like a case by case scenarios.
Okay, thank you. I think we're coming close to the end now. I think we did have another topic, which was to do with what's the most likely scenarios directing the future speed and nature of transition to zero emissions O&M. Does anyone want to say anything about that at all? Any comments?
I think I can briefly pick up on that one, David. Society is driving the reduction of CO2 emissions. We as people are insisting that we reduce our CO2 emissions worldwide. And governments have picked up on that, and that's the whole reason for driving through offshore renewable energy generation. Governments have been subsidising that for a number of years, and I think now no longer need to do it. The developers have taken that on board, and their fundamental goals are all driven about reducing CO2 emissions, and that is in companies like Equinor moving from an oil-based company into a renewables-based company, and it's about big operators like Ørsted, Vattenfall and others delivering to the world CO2 zero emission energy solutions. They are now turning their focus on their supply chain, of which the O&M vessels, the SOVs, are a key part, and they are driving forward the requirement to reduce the CO2 emissions significantly within their daily operations. If you look at Ørsted, I believe they have a target to reduce their supply chain CO2 emissions by 50% by 2032. And that's a commitment that one of the biggest players has made in our industry has made. So we, as vessel operators, CTV owners, etc., we have to respond to that, work with our customers and work with our supply chain to deliver that. And therefore, the drive for CO2 emissions definitely comes from the developers now. And I think that it is a trajectory that we all have to respond to. And I think let's hope that by 2032, we've got zero emission vessels working in our wind farms.
Yeah, certainly. Just to add to that is that we have started seeing that push, that concern now, and we can certainly see that for future projects, the actual consideration of whether a strategy could be more expensive or less expensive, but reduce emissions will start to be a factor on the decision of what vessel or what strategy to go for. So it's very exciting to see this, that society has starting to make those steps of giving priority to these to the environmental factors of the different the different ways of operating wind farms, for example.
I can add a little bit there as well. As we also stated, we design vessels for the next 20 years, 25 years. That basically means that every design we put out now on the market needs to be ready for some sort of alternative energy. So we are actually working very hard on all these solutions. I think that's what NEXUS project really helped to identify the potentials. I also do think that wind farm service operation is one of the areas in shipping that it is feasible to apply certain technologies. Because it is a limited area, you have energy available in the area as well. The energy consumption or power consumption is not excessive either. So it has all the positive points of making it possible to get to a zero emission operation. But it is something that needs to happen now. Basically, all projects that are out there and vessels that need to be built will need to have some sort of strategy. The big challenge is, of course, what energy source, what alternative energy sources will dominate in the end. Of course, NEXUS project looked at using the electrical energy available in the area. But when we're talking about alternative energy sources, hydrogen, ammonia, whatever, methanol, it's more challenging because nothing has been settled yet, and you need to make a decision. You can't design a vessel that will be able to have every single fuel in the future. So that's the challenge I think that we all face and the industry faces today, to come up with flexible solutions that can be implemented also along the way, and still not end up with a vessel that is regarded as way too expensive, for example. There needs to be a different calculation on cost. It can't be just day rate based on the cost of a vessel or the cost of operation. There needs to be an alternative evaluation there.
Yeah, just to take what Martin was saying a little bit further about the costs one. We at Catapult recently did a piece of work for the UK Department of Transport where we asked about the sort of barriers to zero carbon. And one of the big issues is the fuel cost. Now, territorially, many countries are taxing sort of petrol and diesel highly, but with marine grade oil, due to the international nature of it, it's very hard to put any sort of carbon price on that. Whereas the alternative, your low carbon fuels, your electricities or electrically derived fuels like hydrogen, etc., they will often have some sort of carbon price built into their supply chain, whether that's at generation or elsewhere. So somehow we do need to get over that hurdle of the cost of fuels to make this something that, with all the will in the world, people wanting to change, they won't do if they see a huge price cost there. And there is quite a lot of will within this industry, I think, and it's a genuine want to change, because a lot of the business plans of owner operators are based on zero carbon. This is the wind farm industry. This is the sort of future of emissions reduction. So it does look like a good place to start sort of maritime decarbonizations. And the technology seems to be there as well. It's not certainly, you know, future battery technologies, etc., will make things easier and better. But there is a lot of these technologies already in place. It's getting the infrastructure there to help people make these right decisions. So again, looking at fueling, you haven't just got the vessel operators to change their vessels to accept these different fuels. They've got to have some sort of confidence that within port these fuels are going to be available. If they go down the hydrogen route and, you know, 5-10 years time it turns out that all the ports are supplying ammonia, well, that's a huge lost asset they've made. So one of the good things I think about the SOV industry in particular is you do look to have longer charter lengths, and you can look to possibly put collaborative projects in place whereby some of the risk is shared with both the port side, both the fuel suppliers and the vessel operators. And then also in the first instances, you'll have to have some sort of government incentive, some sort of projects to encourage this. Sorry, Martin.
Yeah, that's a terrific point, David. And I think that us poor, hard-worked vessel operators have always seemed to have to pick up the cost of all this new innovation. And I think that it really is something that our industry needs to consider, in that if you look at how the wind farm industry has developed, it started off heavily subsidised by government. We've become efficient in terms of installation and operations, and now we're in a position where wind farms are not subsidised. I think that right now, the cost of technology, the cost of zero carbon technology on vessels, and the solutions are not clear, but the cost has been recognised within this project as being significant. And I think that there should be a drive between governments and developers to recognise the benefits of a zero emissions SOV and work with the vessel operators to drive that forward over the next year. So hopefully in 5+ years' time, there is a solution in place that isn't significantly expensive, that can actually compete with the diesel-driven solutions that we've got in place right now.
I guess it also depends a bit on the taxing scheme. If CO2 becomes taxed, for example, per ton emission, that is then also a factor in if an alternative solution is more viable or not.
I think that's a great point, Martin. I think that if you look at what's happening in Norway, and you have NOx tax, and I think you have CO2 tax, that is going to grow and grow, and that's going to be government driven. I don't think we're seeing it so much in Europe yet, but I think it will. It is likely that will come in, and that could possibly have quite an impact on on vessel operations, and that helps to drive CO2 emissions down, and that's where we all want to be in terms of how we work, how we operate, and how we reduce our impact on the environment.
Excellent. Okay, I think we've that was really good. I think we've come to an end. I think, unless someone's going to say anything at all else, but I'd like to would like to thank the panel there. That was excellent experts who've really started the conversation going, and has got it's got some great thoughts there. So I'd like to thank you all for that. I think, Karina, I don't know any housekeeping. I think I need to just let people know that we have your emails. We'd like to keep those emails off you sent just for the purpose of sending any further information about the project to you. We do also have a video that we were hoping to play at the beginning. We just need to do a few little tweaks to it before we can. So we would like again to send you the link to that, so you can see the video of the project, which is I think going to be very impressive. So is there anything else, Karina, we need to say in terms of housekeeping before the end, or is it?
No, I think that's it. Okay.
So again, I'd like to thank the panel there. Great discussion. I'd like to really thank also the presenters. They did a great job. I have to say, probably a bit biased, but I thought it was an excellent webinar. I'd also really like to thank Karina, who did a fantastic job pulling it all together as well. And I was on the web to talk to her. She was still instructing me what to do at times as well. So thanks, Karina. I wouldn't have been able to do that without you. So thanks very much. But But great, thanks for everyone and everyone else for joining in and joining to the conversations. In terms of the questions, I think we answered most of them. There are one or two I think we probably need to follow up, but I think generally most of them are answered. So thanks everyone anyway. Okay. All right, so I'm going to close the session now, but thanks very much.